So welcome back, and we're going to look at the three exponential distribution examples. I think by now you would have got the hang of it, so I won't spend a lot of time on the details. The first distribution is of the form 1 over theta e to the minus x over theta. You should recognise it straight away as an exponential distribution which has a mean of a theta. And this is for all values of x between 0 and infinity. So one thing I want to do is just draw some diagrams of the distribution. I'm going to do this for each one. I'll try and line them up. So I'm thinking of theta being small here, theta being moderate here, and theta becoming large here. Now, if theta is really small, you can see that x equals 0. The height of this density is 1 over theta, so the density starts off quite high and it comes down very quickly like this. If theta is moderate, then 1 over theta is a bit smaller and it comes down like this. So here theta is small, the mean is small, the mean is moderate here. And then when theta gets really small, it starts off quite low and it goes down very, very slowly like this. So whilst it's always over 0 to infinity, you can see that as theta increases, the average increases, and also the spread increases quite significantly as well. The likelihood here, when we multiply it out, we get a 1 over theta to the n times an e to the minus sum of the xi over theta. So the sufficient statistic is the sum of the xi. That's the sufficient statistic for this distribution. And because theta is affecting both the mean and the spread, it turns out that we need to look at all of the values. We need to add up all of the values in order to get sufficient information about theta. Now, in the second case, the distribution is e to the minus x minus theta for theta less than x less than infinity. So importantly, theta is affecting the range of the distribution here. So when we look at a function of x minus theta, we can really just think what we've done is we've translated the origin of the x-axis to theta. At x equals theta, this is 0. But otherwise, it's going to be the same as the function e to the minus x. So when I graph this, if I graph it for theta small, I've got a small cutoff here. And then I just have the function e to the minus x, which is an exponential with a mean of 1. And then when I come over here and I look at it for moderate values of theta, well, okay, so I'll come over here. So theta's a bit bigger, it's a moderate value. But what does the function look like? Well, it looks exactly the same. It's still e to the minus x. So the shape of it is not changing as it did there. And equally, again, when theta is large, then I'm right over here. But again, it's just e to the minus x, so it's coming down in exactly the same way. So what does theta do to this distribution? Well, it changes its cutoff. It doesn't really play around with the shape of the distribution after that. So if we write down the likelihood here, we have to take note of the fact that theta has to be smaller than the minimum of the xi, and we get e to the minus sum of the xi minus theta times the indicator function that theta is less than the minimum value of the xi. Now we want to write this using the factorization theorem, and so we just have to be a little bit careful here. We can write this as an e to the minus sum of the xi, and then we have a minus theta, so it's an e to the theta, so we have an e to the n theta, and then we have the indicator that theta is less than the minimum of the xi. And what we do is we group this way. And this function is a function of the sufficient statistic and theta, and this function here is RH. It's a function of the data alone, and it doesn't involve theta. And so this factorization shows that it's sufficient for this distribution, the sufficient statistic is simply the minimum. We don't have to look at any of the other values. Okay. The final example we look at is a bit of a combination of both, because in the final example, the density is 1 over theta times e to the minus x minus theta divided by theta for x values between theta and infinity. So we sort of combine characteristics of the other two examples, and let's have a look what happens. So this has a cutoff of theta, but the spread also changes with theta. So if I make theta small, well, sure, the cutoff is going to be in the same place, but the distribution will be like this. It will come down quite quickly because theta is small and 1 over theta is high. So here, yeah, sure enough, the cutoff will move to here with theta, but well, because theta is bigger, there's a rescaling going on in here, and I'll get this shape here, like this. And then over here where theta is large, the cutoff will be up to here, but the distribution will start quite low and will go down very slowly. So this distribution has it's translated, so there's a cutoff. The distribution doesn't start until theta, just like the second one, but also the spread is being affected by theta as well. And given that, you might have some intuition now about what the sufficient statistics might be in this case. But let's just write down what the likelihood is. We get a 1 over theta to the n. We get an e to the minus 1 on theta times the sum of the xi minus theta. And we also get the indicator function as to whether theta is less than the minimum of the xi. Now you can see that in this case we still have an e to the n theta, but we don't have an e to the sum of the xi anymore. We have an e to the sum of the xi divided by theta. This sum of this xi is mixed up with this 1 over theta now in here. So we can't factorize it this way, because this term now has a theta involved in it. And so neither the minimum nor the sum of the xi is sufficient in this case. So the factorization we have to adopt is like this. We multiply by 1. This is our h function. And this tells us that the sum of the xi and the minimum of the xi are jointly sufficient for theta in this case. So we have joint sufficient statistics for theta. In this third example are the two statistics, the minimum of the xi, which is giving us the information about the effect that theta has on the cutoff of the distribution, and the sum of the xi, which contains the information about the impact of theta on the spread. So hopefully this consultation has given you some more insights into the difficult but important concept of sufficiency in statistics.